Hi, today's the day we put it all together. So I actually found another video where a chemical reaction is happening on a scale. So we're just going to watch, we're going to write things down, we're going to see what we have to see. Interesting. I got some information out of that. You saw everything I recorded. So the first thing I want to mention is the 0 button, right? We haven't really talked about technique yet. Depending on the year, you might know this already, but you can put instruments on the scale and then hit the 0 button, and so you can tell the scale whatever you're feeling now, call it 0, which is why when the one beaker's picked up, I don't know if you caught this, the mass went negative because now that beaker was off, and then because it thought 0 was both beakers, and then it went low. So the mass decreased after the reaction. Before the reaction, the two reactants that we had a total mass of 35 grams. And then after the reaction, the total vessel had a mass of 34.2 grams. So there was a decrease of 0.8 grams, and that would be because a gas was released. Obviously, we saw all these bubbles. Yeah, there was a tiny spill there, but that's not 0.8 grams worth of liquid. So the fact that these CO2 gas was created and it left the system, that effervescence, that's what causes the decrease in mass. And that's the number that we're going to use, the difference between them. Something else I think is worth mentioning is that vinegar isn't just a pure substance. It's actually a solution. Vinegar is aqueous acetic acid, so it's this whole substance here. And there is a water that we're not considering in the reactants. That means that the water that's created in the products is new water. It isn't water that was there before. A rearrangement of the atoms to create a new substance, or more of a substance that's already there. It is only the acetic acid that does the reacting, so that means most of the vinegar solution isn't doing anything chemical, which is interesting. But more interesting overall is there's two questions I have. If that's the case, how much acetic acid actually reacted, and did we fully react all of the baking soda? And what's interesting is we can actually figure that out based on the information on the scale. How? Well, that's what we're talking about today. So just to make sure we have all of our data written down, I think it's probably a good idea to pull the molar masses for the compounds involved in the chemical reaction. I'm not concerned today about the sodium chloride or the water. We're only going to focus on the acetic acid, the sodium hydrogen carbonate, the baking soda, and the carbon dioxide. So let me write down those molar masses really quick. So that almost worked out perfectly. Two of the masses ended up being an even integer number there, 84 and 44, 60.1 grams per mole for the acetic acid. And then I also pulled some numbers from the scale. So from this, we can figure out some information. First, the total mass of vinegar is shown here. The total mass of all the reactants is shown here. So taking the difference here, I know that 6.1 grams of baking soda were present before the reaction occurred. Now the question is, does that fully get used? Well, there's only one way we're going to be able to figure that out. We have to look at the amount of carbon dioxide that's released and then come back to talk about what that means chemically for the amount that's used. This is akin to saying, like, if you're interested in baking or cooking, if you were making a batch of, like, chocolate chip cookies, it's akin to saying the 6.1 grams is like saying I have a dozen eggs in the refrigerator. You're going to go make your cookies. That doesn't mean you're going to use a dozen eggs. You can figure out how many eggs that you actually use by the chemical recipe, or the reaction shown here, and doing some calculations in there. How many batches are you making? How many eggs do you need? Do you have any eggs left over? We can see that there is a change in mass. We saw that of 0.8 grams, which is only the CO2, right? We know from the chemical reaction that there's only three products. One is dissolved in water, one is water, and the other one is the gas, and that's the bubbles that we saw. So we have 0.8 grams, and that's the very important number that we're going to use to relate back to all these masses to see what information we can glean from there. Now remember, this 28.9 grams of vinegar is not 100% acetic acid. There's a bunch of this extra water floating around, so we're going to have to do a little bit of math. So this is where stoichiometry really, really comes in handy. Yes, you can convert moles to moles, but scales don't measure moles. Scales measure masses. So that's where we have to step in as chemists and do a little bit of thinking and a little bit of math. So first, to figure out how many moles of carbon dioxide were created, well, we can do that. That's something we did a few lessons ago, converting between grams and moles. We know that we started out that there's 0.8 grams of carbon dioxide liberated. We know 44.0 grams per mole from our previous calculations. This is our dimensional setup. And forgive me, I'm going to fudge your significant digits here to just get one more out of there. I know it's not technically the way to do it based on the scale, but if I were really conducting the experiment with a scale, I would have made sure to bump over to a second significant digit. This is the amount of carbon dioxide that came out. So both of these are in relation to the same amount of carbon dioxide. Using that information, based on our previous lesson, we know how to relate the moles of carbon dioxide to the moles of baking soda. For the purposes of these problems, we're actually not even going to worry about the other chemicals involved. We're only trying to relate the carbon dioxide and the baking soda. If you want to think back to that recipe analogy, that would be like saying, I only am worried about how many eggs and how much butter I need. The other stuff, I have as much as I need with that, but I'm worried about running out of eggs and butter, something like that. So we can write our conversion again, right? We've got our given value, which is in fact the answer from the first question. We've got our dimensional analysis relating moles and moles, and when we're relating moles and moles, we use our coefficients. It turns out in this reaction, there's a 1 in front of both of them, so that the amount of moles of baking soda consumed is the same as the amount of moles of carbon dioxide created. And then finally, we could say how many grams of baking soda were consumed based on that information. So again, we could do this, write our given number, which is in fact our answer from our previous question. And then we write in our values from the previous page. I believe we got 84. And again, I'm going to borrow an extra digit here just for the purpose of comparison. Grams of sodium hydrogen carbonate. So the question is, did we actually use up all of the baking soda? Well, let's go back to our previous number here. The amount of baking soda before the reaction was 6.1 grams. So comparing the 6.1 grams we had to the 1.5 that got used means that we actually had a bunch of extra baking soda left over in that container, which you might be able to see that if you go back and watch the video. It was kind of hard to see for me because the bubbles were opaque, and that was causing it to look like the whole thing was kind of white, so like couldn't really see if there was a white powder in there too, and it was undissolved. But this is what's nice about this process, is by doing this we can actually calculate and definitively say, based on our measurements, that there was in fact a lot of baking soda left over at the time that the reaction was done being filmed. So, short answer, no. This whole process, this is the stoichiometry, this three-step process of going from grams of carbon dioxide to moles of carbon dioxide to moles of baking soda to grams of baking soda. This whole process is the textbook stoichiometry. What is interesting about this process is this is the general form. You can do this in three separate steps, like I did, and if you do go through those three separate steps, you'll see that like the grams will cancel, the moles will cancel, and then the moles will cancel, and you can see all the units fall out one step at a time. But if you've gotten particularly solid with your dimensional analysis, you could actually handle the whole thing in one huge conversion, because the same canceling happens if you string a bunch of these conversion factors together. So let's look at a couple other problems here to see how this all relates. Based on that massive carbon dioxide released, again, it's that 0.8 grams, we can do the whole process again and figure out the mass of acetic acid that was consumed in this process. And so we can relate that back. So this time I think we're not going to worry about the sodium chloride. We're not going to worry about the baking soda. I don't see that in any of our questions. But there is the water for that third bullet, so we'll save that there. But let's write out the, I'm going to try writing out the whole thing now. So the first step is to go from grams of CO2 to moles of CO2, then moles of CO2, and because they're asking, to moles of acetic acid, and then moles of acetic acid to grams of acetic acid. So this is the general form without any numbers. Then we have to go back, and for each of the conversions, between moles and grams, we're going to be putting in the molar masses and 1 mole. The moles, again, are going to be based off the balanced equation. Again, it's a 1 to 1 to 1 to 1 to 1 ratio in this case. And then 1 mole related back to the acetic acid, that was 60.1 grams. So then you grab your calculator. And multiplying that across, we have 1.09 grams of acetic acid. Now the question remains, right, that how does this compare to the mass of vinegar? If we remember back a couple slides ago, I'll just go look. There was 28.9 grams of vinegar in that container. Even at a 5%, that doesn't even line up, because I just did the math, and that is about 3.8% of your solution is 1.09 grams. That's interesting, because that makes me feel like either my numbers were wrong and this vinegar was a little less than 5%. I would wager that I think it's actually 4% for vinegar. I put 5 because I wasn't sure, but I actually think it's 4 now that I'm thinking about it. So 3.8 is pretty close to 4, within the realm of our sensitivity of our scale. But again, this is that long process. You can do it in 3 steps. You can do it in 1 step. I'm actually going to go through this last problem too. How many grams of water were created when that mass of CO2 was created? So now we're trying to relate this 0.8 grams of CO2 back to the water. What's neat about this setup is that for these two problems, substance A is your CO2 for both. Substance B here is water, where it was the acetic acid before. So you can do the same exact setup for the A portion, and then slightly different numbers for the B. Again, it's 1 mole of water because all the coefficients are 1 for this reaction. With a different reaction, it would be potentially a different number in the middle. Those middle numbers are the ones that vary from reaction to reaction. See that first half of the setup is the same, and then it's that second half that's varied differently. From this information, we can also see that in this specific reaction, 327, I believe, grams of water was consumed. So you can see how we can start to put these things together and calculate. If we wanted to, we could calculate how much sodium chloride was dissolved, even without having to separate it from the water. You could then separate it from the water and see how right you were. This opens up plenty of doors to go in plenty of directions. So as one final thing to look at, there's another substance that's very like baking soda called washing soda. The main difference between it is that it's a different chemical formula, but it's very close. Baking soda is sodium hydrogen carbonate, and washing soda is sodium carbonate. You'll notice we've traded out one of the H's for a sodium. It has an effect on the properties, and it has an effect on the molar mass, and it might actually affect this reaction. So if we could write down really quickly, that's the formula for the acetic acid again. If we were to react it with sodium carbonate, we should expect the same chemical reaction to occur. we would still see sodium chloride. You ever realize you made a really big mistake somewhere? I'm going to have to go back and fix that. It's not sodium chloride. It's sodium acetate. It needs to be sodium acetate. I'm really happy that I didn't have any questions having to do with the sodium acetate. Sodium acetate. You get the idea. I'm sorry that wouldn't have made any chemical sense. Anyway, still doesn't matter because we're not focusing on the sodium acetate that's being created, but of course you could calculate and separate. Okay, so we're going to go back and balance. Based on the fact that there's now an Na2, there needs to be a 2 here. That means 2 acetates, which means 2 of these. And then I believe because of that, no, it still comes out the same. So to actually drive home the point, using this washing soda instead of calculating for the sodium carbonate, wow, I'm mucking this one up today. Let's calculate for the acetic acid to not have to calculate a new molar mass. How's that sound? Still, though, we can go through this process because I want to illustrate how this changes when your moles to A to moles to B conversion has numbers other than 1 in it. We're going to assume the same 0.8 grams of carbon dioxide. So the whole A portion will look, again, the same. The big difference is going to be that now we're looking at the coefficients of these two substances, and it's 1 mole of carbon dioxide per 2 moles of vinegar. So the chemistry gets shifted because now that there's not an H in your baking soda, that affects the amount of acetic acid you're going to need to get those H's in place to make that water. So now when you do your calculation, what you get out is about 2.2 grams. Compare that back to what we got on the previous slide, was 1.09, 1.1 grams. So you can see that that molar ratio and that slightly different chemistry means that to make the same amount of carbon dioxide, you actually have to use twice as much vinegar to react with this washing soda as you would baking soda. So again, like you can see how easily we can get into these discussions of you want to carry out a controlled reaction, you want to have a certain target, how much vinegar do you need, how much baking soda do you need, are you using washing soda? It just opens the door to so many questions. So to sum things up, like I said, this process of stoichiometry, it gives you a chance to talk about what can happen, and you can pull information from your final product to go back calculate what did happen. So there's a lot of ability to infer and actually figure out some chemistry here. It is possible. I didn't really talk about this too much. You can see how many moles and how many grams. If I wanted to actually calculate the moles, I would actually just cut off the calculation here. And in doing so, I would have gotten 0.036 moles of the acetic acid. This process can be truncated. You don't always have to go from grams all the way to grams. If you see that you're given grams and asked about moles, you can actually go back and just even cross out one of these, and then you'll just end up at a different ending point. You'll have moles of B because that's the last thing that's in your numerator. So overall, this process can be a little bit much to digest at first, but through a bunch of practice, hopefully the routine gets easier and you start to understand where this starts and stops. You could even hop on at the mole step if that's what you're provided in the problem. Thanks for watching.